All right, this is a really fun topic for me. And it's actually when I started my whole adventure in this field, I started with exploratory factor analysis. Back when I started, I was doing my dissertation, and I love creating surveys or measures. In my research methods class, I have a crazy set of definitions of what a measure is, what's the difference between a measure and a test and a scale and I don't know, a measurement battery. I also talk about the difference between concepts and constructs. So we got to get into all that stuff today, but that's how I started. So I developed this scale. I'm into sports and sports psychology. So my first love was doing something with tennis because was my favorite sport at the time. It still is one of my favorite sports. But so I said, okay, let's develop a measure that would help sports psychologists dealing with tennis players have a way to assess competence, what we call perceived competence, because in the psychological world, you have real competence, objective, like I could have a professional watch my game and say that you're good at this, you're not good at that, you're at this level, etc. Then I could have my own beliefs, and sometimes beliefs are not equal to reality, either in a positive or negative sense. Sometimes people believe they're worse than they are. Sometimes people believe they're better than they are, and those have consequences for behavior. So I thought I'd develop a scale to do that. But my real interest also was in statistics, and I wanted to do an exploratory factor analysis. So I spent my dissertation doing an exploratory factor analysis. Since that time, I've done many kinds of factor analysis, including confirmatory factor analysis and something called exploratory structural equation modeling. So I'm going to talk about all those today, and we're going to get into just the EFA part. So this is something that should be done all the time. Whenever you develop a scale of some sort, you need to undergo a couple of things. When you read most papers, you'll get this, oh, the measure had really nice Cronbach's coefficient alpha. So the Cronbach's coefficient alpha is a measure of the internal consistency. So that's called reliability, how reliable the measure is. But it's a measure of how well the items hold together, but that's not really enough. You really need to do an exploratory and then a confirmatory factor analysis. So I wrote this one paper, which I linked in your course here in the module today. I linked it in here somewhere. Let's see, modules. I linked it in here that I think it's worth reading. I could have had you all read it for today, but I'm trying to keep your workload down. But I call it Navigating the Many Hurdles of Creating a Self-Report Measure. So this is a paper that I had published in this book, somebody's book, and it talks about why I don't recommend people creating a measure when one already exists, because it's a pain in the rear to do this, right? So this is actually would be an interesting paper so to read. And what I did was I talked about it in relation to a measure that I developed on my own. And I just discussed the whole process of developing that measure. And the paper for that measure is also linked here if you're interested in that. It's called this article right here. Or I think this is the article. It could be the measure. Let me see. Let's see what I have here. Might be, oh yes, yeah. So it is the article itself. And I just talk about, I developed the measure over several years, right? And really this is what it takes to develop a measure. Takes years of work to do to make to or to do it correctly. But one of the things that I did here was I utilized something called exploratory structural equation modeling that allowed me to do a better job quicker. And so I'm going to explain all this stuff today and in next session as well. Okay, so let's go back to here. All right, so what is EF? So what is a factor analysis? Factor analysis is a statistical method that researchers can use to look for how many unobserved variables, we call these factors, underlie observed measure variables. So if we look at figure one, right? See, figure one is right here. we have these are items in a measurement scale, right? These are items. That could be how good are you at your forehand in tennis, right? That could be an item. Or my tennis skills are as good as others. So these are actual items. These are objective measures, right? These are the items, and these are what we call factors. So like if in this case here you have, 9 items, and these 9 items represent these three factors: anxiety, impulsivity, and intelligence, right? So those are what I mean by factors. So they underlie the observed measured variables. And I'll talk more about that. Factor analysis has its roots in educational testing with Charles Spearman. If you study psychology at all, you would have learned about Spearman and his, or even if you're into IQ tests, the history of the IQ test is with Spearman's work on general intelligence. He believed there's this G factor that underlies the way students perform in school. So how do you know how somebody perform in school? You look at all of their answers to specific items, and it is believed that those items are indicator of some latent. So latent means something that's unmeasurable. Like intelligence is something that it by itself cannot be measured, cannot by itself be measured, right? We can't see intelligence. You only know it through indicators of intelligence. Like people will say, oh, an intelligent person can answer, a question about the square root of something or whatever in math, or can write a coherent sentence, etc. Or they understand the definition of a complicated word, right? So that's what some people think is an indicator of intelligence. And of course, there's a lot of debate about that, which makes this into an interesting field. Because what are the best indicators of this latent variable called intelligence? And of course, people, took Spearman's work, which was benign. All the work originally was very benign that people did on measuring intelligence. It was made to look at people who had some difficulties cognitively speaking, and then it turned out into this whole industry where people try to get high IQs and go to expensive colleges, etc. Right? So that just changed its way. Okay, so this is where its roots come from. So when people talk about something like intelligence, they are thinking about something that's not measurable, right? So items like test items and even behaviors and symptoms are indicators of what we call latent variables. Again, latent variable is synonymous with factor. So we call factor analysis. We're really doing an analysis of a latent variable. And like I mentioned, there are unobserved entities, and some examples of latent variables would be happiness. Can you measure happiness directly? No. But you can see it through its indicators, like somebody smiling, that means they might be happy, or they're laughing, that means they might be happy, or they're exerting certain behaviors which indicate that they're happy. So all of these things are indicators of something within you called happiness. That's so cool. If you think about the philosophical ramifications underlying this lecture today, it's like mind-boggling. Distress tolerance is an example, like how well somebody tolerates distress. I don't know until I see somebody freaks out in a situation where they need to be calm, right? Disease status. Do you have like type 2 diabetes? One of the questions I ask is type 2 diabetes a latent or a measured variable? It's a latent variable because we don't know type 2 diabetes unless we get the blood work so we see the indicators of type 2 diabetes. Those are all latent variables. So latent variables are only known through their objective indicators. And as it turns out, many, many concepts that we deal with are latent. And we just think that we know them, but we don't. And that's what makes this field really beautiful. Okay, you'll see here that I know indicator variables or measured variables with little boxes, and latent variables are either circles or ovals, right? So these are some of the symbols we use in latent variable modeling, right? So when do we use EFA? Well, we use EFA when we are not sure what the factor structure is. Like I may have thought that all 9 of these items are indicated by one factor, right? Psychological well-being or something like that. So when we're not sure, we employ exploratory factor analysis, right? Confirmatory factor analysis is a second step, right, in the measurement development process. EFA is used when we're not really sure what the factor structure is, so when we get an idea of the factor structure. CFA is used when we know what the factor structure is based on our prior analyses and we'd like to confirm it. As you know, with inferential statistics, we use samples, and samples vary a lot depending on just the random nature of sampling. So since we're not aware of, we cannot assume that the data resulting from one sample will be exactly the same as the data resulting from another sample. We have to redo our studies repeatedly, right, with different samples until we're sure that we have the correct factor structure. So CFA is a method that allows us to verify the factor structure that we got from the EFA. Okay. It's a structural equation modeling method. We can use structural equation modeling, which is something we'll talk about later, to also conduct EFA. We're not going to do that today, but we can do it. And I prefer it in some ways because it really gives me a single number that allows me to judge the validity of my factor structure, which is what our goal is here. We want to know what our factor structure is. When should we use EFA? Well, when we are designing a new measure, right? Or if we're taking our measure and applying it to a new population. Like I've had students, often I work as a dissertation consultant. Sometimes I'm on dissertation committees for students here in our doctoral program of psychology at LaSalle University. And they asked me for help with their analysis. I remember one student who took a study, the Philadelphia Mindfulness Scale, which was developed by one of our faculty here, Leanne Cardasiato, Dr. Cardasiato. And this student took this measure and wanted to have it translated into Norwegian. She was from Norway. And then, of course, because it's a different population, you could technically do a CFA, say, does this work here in this other population? But it's also always, I'd recommend doing the EFA, right? Again, you need to do the EFA and then the CFA. We'll talk later about this method called exploratory structural equation modeling that allows you to accomplish both in basically in one set of data. There's so many ways you can do that, but that's beyond what we're talking about today. All right, so since I mentioned some of these steps, let's go into the steps. I've learned that people love steps. They love to have levels, stages, and stuff like that. It makes life so much easier. So I tend to do a lot of these. I adapt it in this way, right? So let's talk about the measurement development process. Step number one is you generate a set of items to assess a concept of interest, right? Whatever your concept is. So we talk a lot about concepts and constructs, so let's define them. Concepts are abstractions cognitively generated to organize unobserved entities into a parsimonious definition. And I don't know if that definition is parsimonious, but I think it is. It's very stingy, it's a few words, right? Something like happiness, right? How would you define happiness? So it is an abstraction, right? It's something that we generated cognitively using our minds, right? Factors represent concepts. Factors represent concepts. Constructs, people talk a lot about constructs. In fact, we talk about the construct validity of a measure. That's an operational definition of a concept. Operational definition means we define something in a way we can operate on it, like being able to measure happiness. You have to answer this question, that question. So that's my operational definition. Constructs facilitate the measurement of concepts. Questionnaires and tests are designed to assess constructs which relate to concepts. Okay, so it gets more grounded as we go from concept gets less abstract as we get from concept to construct, it becomes more concrete. Okay, so that's your first step. Step two, have individuals assess the utility of the items. Which individuals? Well, if I'm designing a measure to assess competence in junior high school students, physical competence in junior high school students, I should have junior high school students review the items and tell me, are they understandable? Are they too complicated? So this is what we call doing a pilot study, getting some pilot data in there. You want to know, like, can you all understand this? Do I need to reduce the reading level or what? Do they make any sense? Right. Should also have experts in the field take a look at it. Well, when I designed my first survey ever, which was the tennis self-concept scale back in my doctoral program, I had people at the U.S. Tennis Association, USTA, review it and some other coaches and told me, did this make sense? And then they gave me some suggestions. And if necessary, you refine them. I recently also started working on a measure for skiing competence, and I'm still working on that one, but I had some ski instructors take a look at it and they told me what I should do and what I should remove, etc. So that's what you do. You have experts in the field look at it. So you have the people who for whom it's intended and then experts in the field. Right, so those are just items, right? They don't have to be questions like, do you love skiing? Or they could be statements that are evaluated. Like skiing is the most fun sport I ever participated in. True or false or whatever, some scale. So we have to define that measurement scale. There's so many different types, but with factor analysis, we really like to have one of these types of scales, although these are not the only kind. I'll explain in a second. There's a Likert scale. It's pronounced Likert, not Likert. People always say Likert. It's Likert. Respondents are asked to endorse their level of agreement from, say, strongly disagree to strongly agree. So you might have like strongly disagrees at 0, strongly agrees at 7, and then you mark, whatever. Usually they'll give you these anchors to those numbers, or we have variations on that. It doesn't have to be strongly disagree to strongly agree. It could be something like not like me to like me. Like for instance, one measure that I use, one self-concept measure, it's like I am really good at math, and then you have like to mark yourself on not like me all the way to like me. That's like me or that's not like me, right? We can also use a whole bunch of other options. I mean, you can put different faces. Like you see that if you ever go to your healthcare provider and they say, "How's your pain right now?" and they have a smiley face at one end, and they have like crying at the other end, and you pick the face that works for you. You could also have some kind of a ruler, right? It's a 1 inch ruler, and then say mark where you feel. That's actually an interesting way of doing it, right? To use this scale where you mark your placement, because that can be measured and you can get a finer measurement than, say, a discrete scale, like a discrete scale where it's like not a lot like me, somewhat like me, a little like me, etc. You have these discrete values, so you can be more continuous when you have this ruler and have people mark where they go. Conduct a pilot study. So pilot studies, and I mentioned it a moment ago when I was talking about getting feedback from others, but a pilot study is actually where you go out and have people complete the measure. So I might get like 30 or 20 people complete the measure, some small number. I'm also going to ask people again, are the items easy to understand? Is the measure too long? Are there any items that don't belong? So that's another way to get some more data. See, this is a long and slow process because you really, really want the measure to be good. You want it to have internal validity, so it measures what it was designed to measure. You don't want it to be wrong, so you're going to keep on asking questions. You don't want something like as foolish as poor wording to trip up your respondents, right? You don't want them to read your item, say, I don't know what that means. So that if they say, I don't know what that means, then your measure is no good, right? Because it can't have that happen in it. This step, one thing I'll mention here, in conducting all these studies, if I'm going to get 20 to 30 people to do it, do you think I can just pick people out of the street and say, hey, come here and do that? Nah, people want stuff, right? So it's probably going to be hard to get through this step unless you're giving people something like gift cards. So, this is again a very, very time-consuming process. I'll also say try to get somebody to fund you to do that. And I mean that uh, both as a rule, try to get somebody to fund you, but also as kind of being funny here because really try because it's not going to be easy to get somebody to give you money to conduct to design a new measure unless you have a really good reason for it. Like we really, really need this. And often you don't need them because there already are existing measures. Refine the measure if necessary, again, at this stage. Then you go and conduct this larger study to assess the factor structure. There's all kinds of rules about what you should use, how many individuals. I mean, a good rule is 100 participants. Uh, but some people say 5 or 10 individuals per item. So if you have 20 items, 10 individuals, you need about 200 people. It depends. You can actually do this more systematically and run some kind of a sample size analysis using the right software. And then you conduct your exploratory factor analysis. Okay, and that's what we're going to talk about now. The next step after that, of course, would be your CFA, your confirmatory factor analysis. So here's an example EFA here of math competence beliefs. So this is your factor, right? This is your factor, your latent variable called math competence beliefs, and it's believed that. Now notice how these arrows point downward, right? They point downward to the items. So this indicates that these items are indicators of this. They're indicators because my math competence beliefs will impact how well I do in statistics, how well I do in calculus, how well I do in epidemiology, how well I do in chemistry. See, the arrows are pointing from the factor to the observed measures. All right. And I'll talk more about everything else. Or believe me, we're going to get into much more, even those little circles at the bottom. All right. So one of our goals is when we're going to have a bunch of items, like say 20 items or something like that. We're going to throw them into the computer and we're going to expect the computer to spit out a response telling me how many factors are there underlying these items. Like in this case, there's one factor underlying these 4 items. Okay. One way we can do this is something known as principal components analysis, PCA. This is a data reduction method. It identifies the optimal number of uncorrelated equations. So, right. So if we're going to have different equations linking together these items to some component. This is not a factor, though. Component that accounts for the greatest amount of variance in the observed variables. In PCA, the arrows point from the items to the component. So this is an EFA model. So in PCA, you actually have the arrows turned around. So where it's a data reduction method, like if I have a lot of items and want to create, 1 or 2 or 3 items from like 20 items, I could use PCA. These arrows are going to be pointing from here to here, and I'm going to get some kind of a composite score based on relations to those separate variables. Okay. The component is not latent, right? It's not latent. The total number of components will equal the number of observed variables. So for these 4 variables, I'd have 4 components. Okay? So each of them is going to have a stronger or weaker relation to the component, where the items have a weaker or stronger relation to the component. So that's that in that case, we have to select how many components we want to use. Okay. In PCA, extraction employs principal component analysis to determine the optimal number of factors representing the observed items in EFA. You can use it with exploratory factor analysis as well, and people do use it, okay? But just understand that there's a difference between PCA and EFA. There's a really good, there's some good articles explaining the difference. That's something that I think it's glossed over a lot because people are just generally interested in getting their work done. And they're not looking at the nuances. My professor in my doctoral program was really Greg Hancock at Maryland. He was really good at talking about the difference and just understand that they're not the same. Okay, understand that they're not the same. There's another factor extraction method called principal axis factoring. So this is a factor analysis method. So selecting the optimal number of latent variables responsible for the correlation among the observed variables. So here, say again, the arrows are pointing downwards. And this is saying, hey, these items are correlated because of math competence beliefs. So this is explaining why they're related. You see this? Because the arrows are all emerging from math competence beliefs. So that's going to explain why these are related, right? Yeah, right. So this is a- I mentioned this is a lot um like regression analysis, right? Right. So this is this and what I mean by that is like, for instance, this is my in a re linear regression analysis, I'll have an outcome of like say statistics score, and this is its predictor, math competence beliefs, right? So I have this predictor. So my prediction itself doesn't have error, but when I relate it to the observed measure, there are error, and that's what these items are here. This is what we call like uniqueness, or sometimes it's called they're called disturbances. If you really want to get into the structural equation modeling vernacular, you'll call these disturbances, but you can call them errors, residuals, whatever, right? This is the unexplained portion of statistics that, oh, this is the proportion of statistics that's unexplained by math competence belief. So that's the leftover stuff. Some of this leftover stuff can be related to statistics itself, right? Oh, my statistics is, I don't know, something about statistics. How are you? Professor stinks or something like that. And then there's other factors that are unexplained as well. It could be something like, today I had a really bad, or this semester I had a really bad semester because my family was struggling economically. Those are other unique occurrences that can impact the way I would do in statistics, right? So we're expecting that math competence beliefs would have a strong impact on statistics, but it's not the only thing. And see, this is something that you don't have when you're using PCA, because we're PCA, we're just taking the items and creating a component out of it. Here we're actually going from the factor, right, to the item, and we're doing our best to try to predict how you would score on that item, but our predictions can't be perfect. Okay? So we talked about that. Yeah, so I mentioned this, that we call these uniquenesses, right? But you can also call them disturbances, errors, residuals. All right, cool. So that's interesting, right? I mean, isn't that interesting? Well, of course, one of our main goals is to try to identify the appropriate number of factors, right, that are underlying our items. And we're going to talk about two different criteria that we use commonly. One is called the Kaiser criterion, and the other one is using the Scree plot criterion. And for my guide, I'm using this these Pituch and Stevens criteria. This is a book that they wrote. I can't remember when it was written. It was like 1990s, late 90s, or maybe early 2000s, where they talked about these different criteria. And if they still are pretty strong, because we need some criterion to determine how many factors to select. Because you're going to get output, right? You're going to get all this output, and this output is going to say something, and you're not going to know what it says, and you can just listen to what the computer tells you and go, or you can use your own head to evaluate what should be the best solution. All right. So the Kaiser criterion suggests that you select the number of factors underlying the items with these things called eigenvalues that are greater than or equal to 1. Eigenvalues are estimates of variance, right? The sum of the eigenvalues equals the number of the observed items. So you'll see that. So according to Pituch and Stevens, Kaiser criterion is best when you either have a really large sample size greater than 250 individuals, and commonalities are above zero point 0.6, or if the number of variables is below 30 and the commonalities are above 0.7. There's a lot of stuff there, huh? Commonalities, these are the squared fact. We're going to learn all about this stuff. The squared factor loadings from the factor to the observed values. It's like an R squared. So, I mean, you see, we have these paths here, but just like in regression, we have coefficients. So we have coefficients that go along with these paths. Those are the factor loadings, okay? Those are the factor loadings. You'll see that in a second when we run one of these. So the second criterion is something called a scree plot. This is just a plot of the eigenvalues, right? And the with the scree plot, so you have here you have items on the x-axis and eigenvalues on the y-axis. So you want to select the number of factors that are before the elbow. Here's the elbow, right? So the elbow occurs at 2, right? So this is 1, 2, 3. So this would indicate there's one factor, right? I mean, there's minor elbow like right here, but you know that they're pretty much almost flat here. I mean, there's a little bit of a slope, like a green trail in skiing, maybe a bunny slope. Then this would be a triple black diamond jumping down here, right? So Patuch and Stevens recommend the scree plot when the sample size is greater than 200 and most commonalities are large. So the relation between most items and the factor are pretty strong. Okay, sweet. All right, so there we go. So far, so good. So far we learned that you have factors that underlie these items, but we're not so sure how many we should select. And then we're going to use either the scree plot or the Kaiser criterion to select the number of factors. So we do that first, right? Okay, but after that's done, I mean, it's no good to say, oh, there's 3 factors underlying my measure. But what do those factors represent? Like, what does factor 1 represent? What does factor 2 represent? What does factor 3 represent? Right? So we use these factor loadings to define our different factors. One rule is to use the strongest factor loadings, and what's strong is greater than absolute value of 0.4, because you can have negative and positive factor loadings. Here's your factor loadings, here's your commonalities, right? So this is the relation between these variable, this one variable and the 4 factors. So this is a 4-factor solution. This was spit out by a computer program. We've got 4 factors. So we're going to look at, well, we're going to look at these factor loadings and see how do we define this item? Now, this is from my Sims paper. I ended up going with 1 factor here because I think the scree plot came from that paper, right? And one of the things that's important to note about designing a measure and factor analysis is there's a lot of common sense associated with it, especially from people who are in the field who understand things, right? Because you can get solutions that spit out a whole bunch of factors, right? With eigenvalues greater than 1. But does it make sense, right? Can this have clinical use? Like if I have a whole bunch of factors, how's a clinician going to deal with that? I mean, I have to have a nice workbook to explain how to score the measure, et cetera, so they can use it in a clinical setting. Right. So you have to make decisions that are both based on math and the science of factor analysis. I put that quotation marks. I had this English professor who said, don't use quotation marks. It means nothing as for emphasis, but okay. All right. I did it there. Sorry. But you should also use common sense. So it's your knowledge of the field. All right. So like here, let's take a look at this example, like how I would use factor loadings to label my factor. So like here it says factor 1. Factor 1 is usually the factor with the accounts for the greatest amount of variance in the data, right? We'd know about that by looking at the eigenvalues, right? Remember, the eigenvalues have to equal the number of items. I think there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 items here. So if this is the first factor, it accounts for most of the variance in those 14 items. So these factor loadings are going to represent the relation between my item and that factor. Like here, it's 0.001. That's very small. 0.049 is small. 0.398, that's close to that 4 criterion, but not there yet. All right, being a smoker is important to me. 0.672. Okay, well, this looks like it's strongly related to that item. I compare it to its relation to the other item, factors, right? 0.013 negative, 0.161. See, it's strongest here, 0.672, it's strongest. So it probably belongs to this factor, right? If we were going to go with the four-factor solution. I cannot see myself not smoking. 0.803, and no, we're strong again. So my question is, what's the commonality between these two? Being a smoker is important to me. Seeing, I cannot see myself not smoking. It seems like it's something to do with self, me, and identity or something like that. Cigarettes are a big part of my identity. See, that's pretty strong here and stronger than anywhere else. So say I'm starting to get this identity. Possible definition for factor one could be identity, smoker identity. Without cigarettes, I couldn't make it. So this is kind of throws a little bit of a wrench in it, right? Because this one loads here at 0.48, but doesn't load strongly to these others. All right, but we could keep that in mind. Same with, I would feel really empty without smoking, like I lost an important part of my life. So that's, again, a little bit of an identity issue, but it has a zero point 0.4 loading, but it has a stronger loading here, 0.446, right? So it doesn't really belong here, but depends on how many factors I'm going to go with. What else is strong? This one. Being a smoker means a lot to me. 0.684. Smoking is a big part of who I am. So to me, reading those items and looking at that factor, I want to think, hey, this is an identity factor. I know there's this item here. Without cigarettes, I couldn't make it. I guess you can rationalize that as part of your identity. Okay. So that's what we do. So there's a part of this that's an art. It's not just science because I have to go and use my clinical experience. I like the word art. I know people probably don't like that. I would say art, but clinician is good because a clinician is an artist. If you ever been in therapy, clinicians don't use equations to determine what your problem is. They actually talk to you and listen to you and they go on their hunches. So they become artists, right? So they come up with a solution and this whole way of dealing with you because they kind of have this feeling of what's right and it usually works. Okay. So I would call that one identity. Follow up the EFA with a CFA, but on a second sample. Okay. That's one way you can do it. Just find so you can go out and collect data on another sample. So I collected data on 300 people, and I got to go find another 300 people. That's what makes it difficult. That's why I say if you don't have to do this, don't do it. Just use whatever measures are available. There are alternatives, though. One of them would be to randomly split your sample in half, right? And then for the first half, use the EFA, and the second half use the CFA. Another item that method that I like is this exploratory structural equation modeling. It allows you to do two things in one step. One is to assess the factor structure of the measure, and then simultaneously you're doing a confirmatory factor analysis. But even more than that, you can actually do a structural equation modeling. Like here in this example, I did the EFA, CFA in one, but I also had a model where response to these items in the smoking measure predicted point prevalence abstinence in this smoking cessation trial at 24 weeks. So I mean, that's pretty cool, right? You can do all that stuff. Yes. And here and more. Yowza, yowza, yowza. Yeah, you can do a lot of different things. That's what I did here, right? That's a starfighter. I love drawing pictures in structural equation modeling. They look like little animals or starfighters, airplanes, etc. All right, let's keep them going. Yep. All right, so then once you have that, then you're lucky, and maybe if you're doing a doctoral program, you get your dissertation, or you're doing a master's program, you get your master's degree. And then if you're lucky, people will be using your measure, and then you can hopefully have some impact on policy. I'm one of many people who did things with these psychological feelings about smoking. I enjoy doing it, but as far as the research world, most people are like, eh. So it was more of a fun exercise than anything for me. All right, so using the data set SAQ, conduct an exploratory factor analysis to assess the factor structure of the statistics anxiety questionnaire. So this came from a website I found here. It's kind of cute, just talking about PCA versus EFA. So if you, again, if you are ever in need of some good statistics help, I love this advanced for this statistical methods and data analysis site from OARC at UCLA. They're really good. They give you a lot of good stuff. So they have this SPSS. So this was doing things in SPSS. We're using SAS, of course, but we used to use SPSS. So they had this data set called the SAQ, but they had an 8 item version. I used an earlier version that had more items in it. So what was the overview? Let's see of this. Choose a number. I think it's about statistics anxiety or SPSS anxiety. Suppose you're conducting a survey. I want to know whether the item in a survey have similar pattern. I have okay. Yeah, blah, 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 the basic, blah, 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 where? Come on, just tell me about the survey. Let's say they conduct a survey to collect responses about people's anxiety about SPSS. Do all these items actually measure? Here's some examples. Statistics makes me cry. As a professor, I've had students cry in my class. And I didn't do anything to them. They just cried about the stats. My friends will think I'm stupid for not being able to cope with SPSS. Standard deviations excite me. They do excite me. I dream that Pearson is attacking me with correlation coefficient. So Pearson's a jerk. You all know I talk about him being a eugenicist. I hate him for that. I don't understand statistics. I have little, or he was a eugenicist. I have little experience with computers. All computers hate me. I have never been good at mathematics, and so on, right? So let's go ahead and download that data set, of which, of course, as you know me, I already did that in advance. Okay. Oop, I have to re-log in, I think. Oh, darn it. So I'm going to log in here, and from our course setting, you can download. There's actually a couple of these, and maybe we'll see what I decide to do with them. I have the SAQ, and then I have the SAQ with items reverse score. So, but one of the things that you have in measures is sometimes you need to reverse score the items. And the reason you reverse score an item is just to get rid of the negatives, like the negative values. I think, where is it? Here, if we go back to this, some of these items here, like statistics makes me cry. Okay, that means statistics is bad. My friends will think I'm stupid, so higher values are bad. Standard deviations excite me. Higher items values are better in this case, right? So sometimes items need to be reverse score if you want to keep them all on the same scale, where like lower means good, higher means bad, or lower means bad, higher means good. That's up to you. Otherwise, you'll get some negatives. That's so I have a reverse score one as well. So you download from there and get it into SAS, and in this case. It's then, I downloaded it in here somewhere. Do, 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 do. I think it was in here. Let me just make sure it's in here. There it is, SAQ. So remember, when you download it, it first comes in as a .sav, and then you have to import it into SAS. So it's saq.sas7 BDAT, right? You want to be that. Be all you can be. All right, so I have it in there and it's in my MV stats library, right? So MV stats library. So let's go down to the code. This is like some of the easier code you have to do. Look at that. EFA, proc factor, right? Proc factor data equals MV stats dot, so SAQ, that's my file name, and it's in my MV stats library. And I'm using the principal component analysis method here. I'm asking for a scree plot. Oh, I'm going to hold off on this one for right now. And I'm asking it to reorder the output so that I think my higher, I think the eigenvalues or commonalities are higher. So again, I'm newer at using SAS. So let's see what it says here. Reorder causes rows of various factor matrices to be reordered on the, okay, well, we'll find out what they're reordering. All right. And I have 23 items here, question 01 to question 23. All right, so let's go ahead and run this bad boy. A lot of individuals. All right, so here we have our eigenvalues, and there are 23 items. So if I were to add up these eigenvalues, it would equal 23. All right. Um, it's my amount of variance I have. So this first factor, I guess you call it, component, if you will, accounts for 32% of the variance, basically, right? And if we look at this, we have one, two, three, four eigenvalues that are greater than one, right? So if I use the Kaiser criterion, I would pick four factors, right? And this is what will happen, right? Anyway, and that those four items would account for 50% of the variance. I mean, obviously, I can count for 100% of the variance if I were to use all of these, but then that would be stupid. So here's my scree plot. Sorry for saying that. Here's my scree plot. See, the scree plot's a little bit, I don't see the four here. See, where's the elbow? Huh? 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 Where's the elbow? Elbow's right here at number two. So the eigenvalue before that is the first one. So really, this is telling me that one, there's one factor. Interesting. So see, that's a choice you have to make. I mean, if we go by we look at their commonalities are kind of, of course, we're using PCA here. You have to add up to one, but if we look at go back to our criterion, our Kaiser criterion, select the number of factors. Okay, according to Kaiser, best 200, we have more than 250, and commonalities are above 0.6, or if the number of variables is less than 30, which we do have, and the commonalities are above 0.7, they're not above 70, and they're not all above 0.6. Most commonalities are large. I think I'm more inclined, based on this criterion, to use the scree, right? Because look, here's my commonalities. I think most of them are large, but so see, these are tough choices that you have to make. But let's go on and see what this says. All right. What I mean by there is let's look at the ease with which we can interpret the results, right, before we make that decision. All right, so here's our items. Okay. I'll see that they're all sorted with factor one from high to low. Okay. All right, so we have item one, looks like it belongs with factor one. All computers hate me, belongs with item one. I weep openly at the mention of central tendency. Bastard, you shouldn't do that. That belongs in one. These all belong in one. Wow, they're all pretty clearly in one. Interesting. So, with the exception of maybe one item, everything seems to belong with one. This item, my friends are better at SPSS than I am. It doesn't load well. And this one doesn't load well either. My friends will think I'm stupid for not being able to cope with SPSS. So there's a few items that load on different factors. But I mean, see, I can see a case for using a single factor model here because it tend to load pretty well on this first factor. I mean, you have this item here that doesn't and these that don't. And what do you do with those? I mean, do you eliminate them or do you in the pruning process or do you do you change something? Let me see. Let's take a look at what would happen if I use the one where, I mean, I know what would happen, but I just want to see what the make them positive just to see that, to facilitate my ability to understand everything. So let's download this one here and download. Okay. Well, let's download this bad boy. We'll call it SAQR for reversed. Okay, so let's go to SAS. You can watch me do this again. Let's see, Let's download. So I'm going to click upload files or upload, not download. Choose from the computer, and this is in my downloads. Here it is. Open. Upload. Let's take this and where is it? I should say something reversed, right? SAQ reverse. Here it is. I'm going to import that data, those data, excuse me, and change the names. Let's change the name. Where's the split screen? Where's the split? There it is. Change name. Put this in my MV stats file library, sorry. And then I'm going to call it SAQR for reversed. Let's save. And then we'll run this. All right, so let's rerun everything again. I don't need this anymore. Don't save. My code, and let's run this again, but we'll use the SAQR data set instead. SAQR. There it is. All right, let's run. Run, Forest, run. All right, so now we'll just get this. So is this just want the interpretation. All right, so now with the, there we go, look at this. Did I do this right? I hope I did it right. It seems like I didn't. Doesn't it look like the same? Okay. Maybe I didn't do it right or something. It should be different. Okay, but let's, I thought they were positive here. They're negative, because weren't they negative before? All right, well, I'm not really sure if I did the right thing there or not. I read what I had in there. All right, but okay. But anyway, I'm leaning towards a one factor solution. So let's go and try this. Let's try the one factor solution. Let's try the one factor solution. All right, now if I can remember the code for that. This n factor, yeah. N factor, it says here, specifies the maximum number of factors to be extracted to determine the amount of memory to be, okay, fine. We'll do that. And we're going to extract one factor because that's what the scree plot said. So here's my one factor. Look at that. So can I use this? And again, I think I must not have rearranged those. Maybe I did this data set a couple of years ago, so maybe I forgot to reverse score it. If I wanted to reverse score it, I can create a new data set and just do 1 minus or whatever the, 1 minus whatever the value or whatever the top value is, and they'll reverse score it. But I'm not going to do that right now. But okay, so those items taken, if I'm good at statistics, my friends will think I'm a nerd. My friends are better at statistics than me. What happens if we do a 2? Let's try 2. The reason I'm thinking of 2 is I wonder if those negative values will load onto a second one instead. Let's try that. 2. see what I talked about, the art part of this? Interesting. Look at that. All right, these are the negative ones. One of the things I want is I want to have a lot of items that have higher factor loadings, above zero point 0.4. And here I only have three that are above zero point 0.4. Well, actually at four. So I don't know if this makes for a good second factor. If I'm good at statistics, my friends will think I'm a nerd. I can't sleep. I can't sleep for thoughts of eigenvectors. Everybody looks at me when I use SPSS. Is that a good thing or a bad thing? My friends are better at statistics than me. So reverse would be and I think personally I would probably just use a single factor solution here. That's just based on my, I mean, because why do I need what am I going to say? There's a factor for social relationships with SPSS or what people believe about me. I think I feel better. I feel more confident with that one factor rather than having two factors. So hence, this is what I mean by the clinical or the intuition or even the experience part of developing a measure, right? Is you use your understanding of the field and your history to solve it. Then if you want to reverse score these, you can to make them a little bit better. Or you can even say, hey, maybe these items just don't belong, right? Like this item, if I'm good at statistics, my friends will think I'm a nerd, right? That's only a loading of 0.14 here. Some of these loadings are really low, so maybe I could, maybe I really don't need them, right? So that's what part of the process is when you're developing a measure. You got to go through everything. So this is actually a lot of fun. This is fun to do. And I did it for my dissertation, and I had a blast doing this. Before we had decent technology in 1997 and 98 when I was finishing my doctoral program, but not like we have now. So this is so much fun to do, and it's part of the being creative process. And if you're a type of person who likes to name things after you, you can name the measure after you. I don't go for that stuff. I just name it after whatever it is. But anyway, yeah, so I'm going to stop the recording now. Hold on, Sophia, don't go away yet. I'm going to stop the recording. Yes, I. Yeah, yeah, yeah.